Hey, what's up, guys? This is Chung here again. So, continue on the LeetCode problems here today. Today, we're gonna talk about this number 99, recover binary search tree. This is marked as a hard problem, I think. For the native naive uh, log n solutions, I think it's kind of like a medium-ish level problem. But anyway, let's go right into it. So you're given a binary search tree, but two of the elements, two of the nodes in the binary search tree are swapped by mistake or intentionally, who knows, right? And you need to recover the tree without changing its structure. Okay, so basically you need to change those two swapped node back to before they were swapped, right? For example here, so 132, right? Okay, so first you guys, I'm pretty sure you guys all know about binary search tree. For the binary search tree, all the nodes on the left side, each node, the left side node has to be smaller than the node itself, and the other right side node should be greater than the node value, right? So in this case, 132 is not right because 3 is bigger than 1, right? So in this case, so which are the two nodes that got swapped? And obviously it's 3 and 1, right? So basically, if you swap 3 and 1, then we got uh, a valid a binary search tree. Same thing here for here. So 3, 4, 2, and so 2, 3. Yeah, basically the 2 and 3 got swapped, right? So you need to change it back to 3 and 2 and 3 here, and then it will become a valid binary search tree. So I think the easiest way or the most intuition way will be do pre-order a pre sorry an in order traverse, right? So remember, with for a binary search tree, if you do an in-order traverse, the value should be sorted, right? Should be increasing. Basically, if you traverse the tree in order, so in this case, it's going to be 1, 2, 3, and 4, right? So you'll be getting a sorted array. So with that in mind, so what we need to do is we just need to use the pre-order traverse. Right? Pre-order traverse, we traverse the left node, the root, and then the right node. We need to use the pre-order traverse to find out those two nodes that that are I mean were swapped, and then we just need to get those two nodes, and then we just swap those two nodes value, right? Yeah, so let's get to the coding, right? So with pre-order traverse, uh, we have two ways, right? Basically, the first way is gonna be the recursion, right? And then the second one will be the the iterative way, which will be using the stack, right? So let's see. I will try to do a recursion here first, right? So it's gonna be since the recursion is the easiest way, right? So you're gonna have a DFS, not DFS, def define in order, right? In order traverse, right? It's gonna be the node here, right here, and then what? And then like what we discussed, we need to have those two variables that will be storing those two swap nodes, right? We're gonna have a first and a second and a pre. Yeah, okay. I'll explain about the pre later. So What does pre mean? Pre is the because during the traverse, right? I mean, let's say the traverse here, for example here, this 1 2 3 4, right? So ideally the traverse should have 1 2 3 4, right? But in this case, for example here, so it's gonna be 1 3 uh 1 3 2 4, right? And so that's what happened, right? So I think the reason we need a pre-node here is that we need to we need to maintain the pre-node for each node. Let's say three, the pre-node for three is one, right? And the pre-node of two is three. So we need to check every time when I see if the current node value is smaller than the pre-node, then we know this number or this number has to be is one of the is one of the those two swap numbers, right? That's why we need to keep maintaining this pre-node here. Cool. So continue with our in-order traverse here. What does the in-order traverse do, right? So if first, if not node, right? If not node, we simply return it, right? Because if it's nothing there, there's there's no need to keep doing the traverse. So what does in order do? In order do is we need to go all the way to the left, right? So basically we need to go all the way left, node dot left until we reach the leftmost node, right? And then we come back here. We come back here, we do a now the node value is we're gonna do something here, right? Do something with the node value here. And then after we're doing the current node, we'll go to the right side, right? Right node dot right. That's the in order recursion traverse, right? So what are we doing here? So we check, right? We check the okay. So first, if the pre-node is not empty, because for the first node there's no need to check, right? And the node current node value is smaller than the pre-node, right? Pre-node value, right? So if that's the case, what do we do here? Okay, so non-local first, second, pre, right? So if it's not there, then what? Then what? We just assign the first node to the current, right? And then if not second, right? If not second, then we just assign the second node to the pre, right? So either one is them is either pre or the actual node itself. So else break. I'll explain this one here. Let me finish this one here. And then in the end, we're gonna do what we have to updating this keep updating this pre-node, right? Yeah. So the first part is pretty obvious because every time when we see this the first node and remember we only check this first try to assign it first and second when the current node is not is smaller than the first one, right? Uh, let's say if this 1 2 3 4 5 6, right? No, this is not a good one. Let's say this 5 3 4 2 6. Okay, let's say for example this one, right? So the 2 and 5, those are the two numbers that got swapped, right? So that's how see that's why we so the first time we're seeing this, okay, the current one is smaller than the previous one, then we're at this point, right? So we're at this point, then we assign the first one with the current one, which will be 3, right? Which will be 3, but then we assign the second one to be the, if second one is not none, but at this moment the second one is not, right? So we assign the second one will be pre, right? So now the first one will be, first one is 3 here, and the second one is 5, right? So now we have the second one here, right? Remember here, we only assign that if there's not assigned before, right? So the second one is 5, which is 5. So now the first one is 3, which is not, it's not correct, but don't worry, right? So we're not done here, because we'll be, since there are two numbers got swapped, so, and we'll be entering this one twice, right? In this case. So in this case, when it reaches the second one here, right? The second one here, so this is the current, right? And the previous one is 4. Now we we keep like assigning this current one to the first one. Now this one will become the first one. But the second one will not be assigning the second one to this 4, because we have a if check here. So that's why this one will work. And here, the break sign here, right? So why do we need a break here? So that's actually a small trick, so we can terminate this in-order traverse earlier, because if this one has already been signed once, and the second time when we see it, because we only need to traverse, we only need to find those two numbers, right? So when this one enters else here, we know that we have seen this conditions twice, right? And then we can just stop, break it, basically. Okay, so that's that. Okay, and once this is done, we have the once this traverse is finished, we have this first, second, right? And then the rest will be very easy. So okay, in other routes, right? So we need to do a route. The rest will be just swap the values of the first node and second node here. Yeah, second and the first, right? I think that should do it. Okay, let me do a quick check here. First, second, pre, in other, have other, okay, in other root. Okay. Sorry, okay, what I'm thinking. So it should be return, sorry. So since we're doing the recursion, not the iterative way, so here should be return, not a break. Sorry, I was confused about the while loop, the ones we'll be talking about next. Note. Yeah, okay. Cool. So this one works, right? So pretty straightforward. And the second one is the iterative pre-order in-order traverse. Yeah, I think that's something you may also get asked, because this recursion is very intuitive, but sometimes you are asked to if you can implement this in a non-recursion way, right? So how are we going to do it, right? Same thing here, right? So that we need to use a stack instead to do a in order, right? Traverse stack, and what do we have a current here? It's root, right? So with the now the we need to define those variables at the beginning. So what do we do here? Same thing for the recursion, right? So we need to use a while loop. Well, current or stack, right? So what do? We need to find, for each current node, we need to find the leftmost node, right? Just like what we did in the recursion solution. While current, right? So we do stack dot append current, and then we just do current equals to current left, right? Because basically we keep pushing the root node until we reach the end of the left side, right? So now since we're doing the current here, so while the current has a left side of the root of the node, we just keep going to the left, and meanwhile we just keep pushing the root node. Why we keep pushing the root node? Because once we finish with processing the sub node, we need to find a way to go back to the root node so we can process the right side, right? Because we need to process the left side and then the root and then the right side. So we need to uh, basically remember the path. How did we get here? So once we reach the left side, right? So what do? We pop the first one, right? We pop the first root, pop pop it, right? And then same thing, right? Same thing with the recursion. We check if pre and pre if pre is not empty and the current, right? Dot value is smaller than the pre, right? Dot value. We just do the same thing, right? It's the first. Doesn't really matter which one is first or which one is second. We just do a current one, and then if not second, we just assign the second one. Pre, right? Else we just break. Else we break, and then right here, remember we have to keep maintaining this pre node, right? And then once we process the current node, what do? We need to go to the right side. Remember how we did in the recursion? So we need to assign the current one to the current dot right, right? That's how we move to the right one. So once we have the right node, we'll go back here again, right? And then we'll go for the current for the right node here, we'll go again, try to go to the leftmost node of this current right one. So that's how we do the traverse, right? And yeah, okay, I think that's pretty much it is. Yeah, same thing. Cool. Yeah, that's the iterative way of doing the in order traverse. So the remember here, so two things to be noticed here. So first one is here we do a current or stack because we start from the current, right? So we need to use the current because every when we reach because in the end, see in the end we set the current one to the current right one, right? So if this one if current is not is empty, if the right one is empty, there's no need to stop. There's no need to continue. Uh, sorry, yeah. So but sorry, this is the or here. So basically, if there's anything, if the current is not null, or the stack is not empty, then we continue, right? because because here, so let's say even though the right side is empty here, if this one is not, right? But let's say we still have some unprocessed node in the stack here, and then it will go here. So the current will be empty, so it will skip this one. But then we'll pop the next available node from the stack here. That's why we need to check both here. We check both. Either of this one is true, and then we continue. Okay, and so as you can see here, that's the it's obvious for the either stack or the recursion. The the time complexity is O(n), right? And the space complexity is also O(n) because with stack we store each node up to n nodes into this stack here, and the recursion same thing. Since recursion will also uh, use the O(n) space because we have to have n recursion call, right? And so now here comes a interesting follow-up question here. Could you devise a constant space solution? Which means, can you use an O(n) space to solve this problem, right? Can you? Yes, of course you can, but that will require a new approach. So the new approach is called Morris traverse. So the Morris traverse, what does it do? It's basically it doubles the time complexity from O(n) to 2O(n), which is still like a big O(n), right? But then it will not use either recursion or the stack. How, right? Let me draw some picture here. Let's say, for example, here the two. Let's see. Do we have a better example here? Let's say we have a 6 here, right? 6, 8, 10. 3 here. 5, 2, and 1, right? Sorry. Here, 1 and 2. Yeah, I think this is a better example here. 1 and 2. Yeah. So the reason we need for the either stack or the recursion is that we need to remember how did we come down here? Like how did we come down here, right? Remember that? So when we were process 3 here, once we finish processing all the node for 3 here, then we need to go back to 6, right? That's why we use a stack, because in the stack we push 6 first and then 3, right? So once 3 is popped, then the next one will be 6, and then that's how we remember how can we go back to the previous parent node, right? The recursion, same thing, right? The recursion automatically does it for you, because it's a re, it's a re, it's a recurse automatically recursing. So once the the inner level is finished, it will go automatically go back to the previous call, basically, which is 6, right? So what does the Morris traverse algorithm do? Basically, it maintains it uh, maintains a link from the left side subtree and the current node here. So basically, every time when you need to process the side tree, you need to find once the tree is finished processing, you need to know how can I go back to this parent node, right? How we need to we will establish a link from the rightmost node of the left subtree to the root node. Why? Okay, here's why. Remember, each subtree is also a binary search tree, right? And for binary search tree, remember, we're doing in order traverse, which means from this subtree, we're also doing a in order traverse, which means the rightmost node will be the last node to be processed, right? For this left subtree here. So what does it mean? So for left subtree, the 3 is the 3, right? So 3, 1, 2, right? So what do we process? We process 1 first, right? 1, 2, 3, and so 5 is the rightmost. 5 the rightmost node of this left subtree, right? Then we will just need to build a link from the 5 to 6, right? And once this link is built, then once we finish processing this 3 here, right? Remember, so each 3 will have a we will create a new predecessor. We have a predecessor node here for for each of the this node here. For this node, let's say for each node here, we'll have a predecessor. The predecessor will store the information of the rightmost subtree. Basically, the predecessor of the 3 here will be 5, and the 5 that are on the right of the 5 will be 6. So with this information attached along with this node here, once this node is finished processing, we know the next one we want to process is 6, right? That's how this Morris traverse work. Okay, so let's try to implement this. Just stay with me, guys. I'll try to explain this one. And so predecessor. Okay, since without this pre here, so we're gonna create a new predecessor predecessor node here because this pre-node will be using the pre-node to find the swapped nodes, right? That's why we need like another predecessors, like I said, for the to remember, right? To create the link, to create the link between the current node and the parent node, right? Since no more stack here, right? And current, okay, I'm gonna keep this one. So if no more current, so what do? We do a simple while loop. So remember, so for each node here, right? Like what we discussed, first we need to check if there's a left node because we only need to keep the value the link from the left side because the left side, remember, that's when we need to know if we how can we the then we need to know the parent of that left subtree because on the right side we can simply going down to the right side. We don't have to go back, right? Because when we reach the 6, let's say the left side is already processed, and then when it goes down to the right side, we don't need to know the parent because remember that's the sequence, right? It's left, root, and right? That's why when we process the left one, we need to know the root because the next one we need to process is the root. But now then when it comes to the right side, right side is the last one. We don't care about the root the parent node anymore, right? Okay, so okay, I'll try to explain it. So first we check if the left side if the current has a left, right? If it doesn't have a left side, uh we can simply just ignore it, right? There's an else here. I'll keep an else here. So if there's no left tree, we don't need to maintain that's the parent link, right, with this predecessor node. Okay, if the left side has a if the current one has the left side, so what do? First, we need to find the rightmost node of this left subtree. How, right? How do we do it? We just use this predecessor here. We assign the left side node to be the predecessor first, equals to current left, right? That's the starting point, right? And then while the predecessor has a write, right? When it has a write and that's not equals to the current one. Okay. The first one is pretty easy to understand because we wanted to keep doing it, but why the second one? Because when the next node comes to here, right? So it will go again here, it will go again, right? And here, because since once this process finish, we'll be creating a right side. We'll be creating this. We'll assign this current to the predecessor's right. And if we don't check it here, the next time when the next node comes to this while loop here, once so this processor's dot right will never be will not be empty, and it will keep going back to the current to the root node and then going to the right side, which is wrong, right? Uh, dot right side, right? Okay, so at this moment we have the rightmost the rightmost node, right? For the current node, right? Okay, then what? And then we just and if not, right? So we only establish the link when when it has not been established before. When there's not right, when it's not there, we do what? We do a we assign we basically we establish the link here, current, right? That's how we establish the link here. And once we establish the link, what do? We keep doing this to the left, to current dot left. Because why? Because we want to. Okay, let me bring back that node here. Oh, it's not here. Right. So now we have this link from 5 to 6, right? But then we don't want to stop here because and we want to basically we want to find we need to keep looking to all the left side node, and we want to build the link for all the subtrees as well, because once we have all the subtrees, then we can start processing using this link to process to traverse the tree, right? So we have to keep going basically from here. Once we establish the first one, we just need to assign the current one to the current left. Basically, once this link is done, right? 3, we have the rightmost node is 5 here, so we establish the link from 5 to 6. Then we just move forward to 1 here, right? From 3 to 1, because that's what we do. Current equals to current left, because we also need to want to build any link for the 3 subtree, right? So for with node with root node as 1, the rightmost link, the rightmost node will be 2, right? So what do we do here? So we build another link from 2 to 3 until we reach the end of of the left side. Okay, and so that else, right? Else do what? Else basically else is done. Else we can just process the current node, right? We can process current node, right? And then how do we maintain, how do we keep processing? How do we process the current node? Once we process the current node, once we finish processing it, we have to do what? For the current node, we have to remove the link, right? Because we otherwise we'll have a like we'll have a cycle in the tree. Predecessors dot write equals to null, right? That's how we I mean recover the tree from to its original status. And then we just do a current equals to current write, right? Okay. And here, so okay, so basically we have this basic structure here. That's basically how the Morris traverse work. Yeah, so I would try to go through this algorithm first before adding our swap logic to this code first. Yeah, right here first to help you understand this how this Morris traverse will work, right? See. Okay, for example, remember here, so at this moment here, remember we just keep traversing to the left until we have built all the linked at this moment, right? So at this moment we have a link from 5 to 6, right? And then we have a link from 2 to 3 here, right? So how will this thing work, right? Remember here, so once we process 1 here and 2, right? So once we process 2 here, we you know I would because here I think I need to finish here. So this is the current. That's how we do a I need to add this one here. That will be the complete algorithm here. So if there's no left, if there's not left and not there's no right here, right? We go to the right side. Let's say here. So once we build all the link here, so the one will be the first. So basically now the current will be one, right? So the current is one here. The current is one because the one will be the first element will be really processing, right? So then where would it go? Because the current is one, and does current has a left here? No, it doesn't, right? Then it will go to the else here, right? It will go to else here when we process one. So now the current becomes two, right? The two here. When it becomes two here, and then it will go back here to the current here. It will go back to current. Does two have a left node? No, right? And then it will come down here again, right? So remember, notice here. So we do a current dot right. So now we're doing the right, the two dot right equals to current, right? Remember, we already have a link from 2 to 3, right? So now the current will become 3, right? So now is the current here. That's how we use this predecessor link so that we after processing 2 here, we can go back to 3, right? Because of this. Okay, now I'll show you why this is necessary. So now we have 3 because modifying the, we're not changing the tree structure, right? So now we're processing 3 here. Does 3 have a left node? Yes, right? 3 has a left node 1. And then we'll go to the, well, basically it will repeatedly doing this, right? We'll try to find the rightmost node for the 3, right? And then we'll get 2 again here. So the reason why we're repeating the same logic over again for the 3 here because once we process 3 here, we want to remove the link for 2 because we don't want to keep it. So the how when can we remove it? So when we process this parent node, once we process after we process this parent node, then we know we can simply remove this link because we don't need it anymore, right? But and this logic is help us to find out this like this predecessor node here, and that's why we need this one because at this moment we do a predecessor right, we keep doing to the right. Sorry, yeah, so here's the right side, right? So the left current is 3 here, so we start from the left here, which is 1, and then we go 2, right? So now the 2 here, right? But the 2 dot right is current, right? Because we are at this moment we already have a link here. If we don't have this, if we don't have this end here, what it will do, it will continue go back to 3, right? So now the predecessor will become 3 because the predecessor dot right exists, right? It will be 3 and then 5, right? Then will be go some other places which we don't want. That's why we need this check here to stop until before once we see this 3 here, right? And once we find this the rightmost node here. Okay, so here that's why we need to have a not set here because at this moment it's already set, so there's no need to do this logic again because that will go back to the left again, which we don't need, right? So then it will in this case it will go to the else here, right? So then we can start processing this node here, the 3 node, right? And once we process 3 nodes, like we said, uh, besides doing this regular um, movement from current to the right side, we also need to remove this link from this 2 to 3, right? That's how we remove this link. And then we go back to 3, and then we we move to the right side, I mean, which is 5, right? And then the 5, the current is 5. Does 5 have a left node? No. It will go, it will continue to the right, which is 6, right? See, which is 6 at this moment, 6. So and then it goes back here again, same logic here. 6, does 6 have a left? Yes, it has a left. So it will go back here to check to find basically the child node of 6 here, which is 5, right? Then once you find it, oh, it goes over and over and over. Yeah, that's how this Morris in order traverse work. Hopefully you guys understand it. And now we have this traverse code here. Now we can just simply add our swap code here, right? Remember, we still basically we just need to add this logic, which we already seen twice previously, and to here, right? Okay, so we already have that. So remember, we have 2 places. We'll be doing the regular process, right? This is to process the leaf node, and this else is to process the root node, right? So we have to duplicate the same code in 2 places. So we will be maintaining this current, right, as the previous, and same thing here if we have seen if current less than, right, the previous dot value, then we just do what first or second, whatever, current. If not first, we do a first dot pre, right, dot pre, and else no. Okay, so here, remember here, so we cannot do a else break here. We cannot do a else break here. Why? Because if we break before traversing the whole tree here, because the and let's see we have let's see the swapped two nodes will be down the road, very deep, somewhere here, right? Somewhere here. Let's say there are two nodes got swapped here, and we'll be getting those two nodes from this logic. Once we get this logic, let's see if we just stop here, break here, right? So what does it do, right? It will stop here. Basically, we'll have we'll leave all this kind of parent, the predecessor and the parent link here, right? Which will make this tree a cycle, right? Which is not right. So which means even though we have seen those two swap nodes, we cannot stop here. So we have to keep finishing processing of the tree to remove all the predecessor's link we previously established. That's why this Morris uh, algorithm is kind of like a little bit time consuming, but it it, it will save us a lot of space because it doesn't use any extra space here, right? So basically we just simply ignore that break here, right? And we can just copy the same logic here, right? Yeah, we just simply copy the logic here, and then that's pretty much it is, right? So that should do the job, right? So once we finish everything, it should do it. Run it. Predecessor is not defined. Yeah, I'm pretty sure there are some typos down there. Cool. Yep, works. Cool, guys. So just to recap what we have discussed, Morris, right? Morris algorithm. So what do we do? Every time we see a node, right, we check if there's a left side. If there's a left side, we try to find the rightmost node of the left side, and then we establish, right? We establish the link from this rightmost node to the current one, and then we just keep going down, right, until we had established all the link, and then we just do the process, right? Remember here, every time we finish the process of the a root node which has the left side, right? We need to remove the node, the link, and then keep going to the right side. Same here. If it doesn't have a left side, we just do a regular process, right? Cool, guys. I think that's it for this problem. Thank you for watching the video. Cool. See you guys. Yeah.